Lecture 7, Formulation of Issues and Constraint. In this lecture, we're gonna discuss third part of first, the third part of the system engineering life cycle, the concept definition. And this is material that is in chapter 8 of your textbook. The agenda for this lecture is start with selecting the system concept, the performance requirements analysis, functional analysis and formulation, functional allocation, concept selection, and then finally we're going to speak briefly about unified modeling language. So the output of this phase of the system engineering lifecycle model is a specific configuration that will constitute the baseline for development and engineering. The selection from a number of alternatives system concepts, and as you can see in this diagram, we're moving from concept exploration to concept definition. So from this point on, we are going to be specifying some system functional specifications, and we are also going to provide some defined system concepts. This phase constitutes the last phase of the concept development stage and leads to the initiation of the engineering development stage. In terms of the materialization status, we are now in the concept definition, which is the fourth column of this table. On the selection and functional definition of the system components, so as you can see now we are into, if you look at the column that says concept definition, as part of the concept development phase, we are now a step further into the hierarchy process. We are now allocating functions to components. The definition of their configurations into subsystems is also part of this materialization process. So this is the column that I was referring to. The system engineering method as part of the concept definition, as we've been doing for the previous two phases, for the need analysis and the concept exploration, we are also going to go through the system engineering method as part of this concept definition phase. So starting with the performance requirement analysis, typical activities include analyzing the system performance requirements and relating them to operational objectives, refining the requirements as necessary to include unstated constraints, and quantifying qualitative requirements where possible. As part of the functional analysis and formulation, typical activities include allocating subsystem functions to the component level. So as I mentioned on the previous slide, we are going into that level of the hierarchy of the system design in terms of system functional elements and defining element interactions, developing functional architectural products, and formulating preliminary functional requirements corresponding to the assigned functions. In terms of the concept selection or the physical definition, typical activities include synthesizing alternative technological approaches and component configurations designed to performance requirements. So here we're going to start out looking at the technology, developing physical architectural products, and conducting trade-off studies among performance, risk, cost, and schedule to select the preferred system concept defined in terms of components and architectures. So at this phase, we are trying to address that technology. We have an idea of how the system should look like in terms of a higher level. Now we are trying to allocate technology to those functions that needs to be performed by the system. And we are going to conduct some trade-off studies in order to know which of the alternatives or the concepts is better to push forward into the next phase of the system life cycle, systems engineering life cycle model. In terms of concept validation, some of the activities include conducting system analysis and simulations. So we talk about simulation using this math theory that we discussed on the previous lectures to confirm that the selected concept meets requirements and is superior to its competitors. Also refining the concept as may be necessary. So as we've been doing for the two previous phases of this systems engineering life cycle, we had this diagram that summarizes the how the systems engineering method is implemented for this particular phase. So for the concept exploration phase, we have how performance requirement analysis, functional analysis and formulation, concept selection, and concept validation. Second item of the agenda looks at performance requirement analysis. So at this point, we want to look at the analysis of the stated performance requirements. System performance requirements, as initially stated, often represent imperfect interpretation of the user's actual needs. Essential that both the basis for the requirements and their underlying assumptions be clearly understood. Steps can be taken to refine the requirements as necessary to support the definition of a truly viable system concept. So keep in mind that the output of this phase has to be a viable system concept that we are going to push forward to the next phase. System lifecycle scenario. It is necessary to develop a model or scenario that identify all of the different circumstances to which the system will be exposed. And we've mentioned this before. This includes at least 1. Storage of the system and or its components, transportation of the system to its operational site, assembly and reading the systems for operation, extended deployment in the field, operation of the system, routine and emergency maintenance, system modification and upgrading, and finally system disposition. This has to be sufficiently detailed to reveal any interactions between the system and its environment. For example, the maintenance of the system will require a supply of spare parts, special test equipment, special test point, and other provisions that need to be recognized. In terms of the requirements and the predecessor system offers an excellent basis for understanding the exact nature of the deficiencies that led to the call for a new system. A point of departure for quantifying the requirements for a new system. Documentation available that can provide a direct comparison to requirements for the new system. Okay, so now that we have an understanding of how to work with this performance requirement analysis, we can move to the functional analysis and formulation. So we need to start by defining the component functions. Concept definition phase is mainly concerned with the functional definition of the system components. Functional building blocks is translating performance requirements into system functions that can be illustrated by using the concept of system functional building blocks. First, we start by identification of functional media, which includes the type of medium, signal, data, materials, energy, and force involved in each of the primary system functions, can usually be readily associated with one of these 5 classes. 2. Identification of functional elements. Operations on each of the 5 classes of media are represented by 5 or 6 basic functional elements. The system actions or functions can be constructed from a selection of those functional building blocks. And we discussed those in one of our first lecture. Relation of performance requirements to element attributes. Each functional element possesses several key performance attributes: speed, accuracy, and capacity. If this can be related to the relevant system performance requirements, it confirms the correct selection of the functional element. Configuration of functional elements. The functional elements selected to achieve the required performance characteristics must be interconnected and grouped into integrated subsystems. This may require adding interfaces, input-output elements to achieve connectivity between these subsystems. Analysis and integration of all external interactions. The given performance requirement often leave out important interactions of the system with its operational or other environment. This interaction needs to be integrated into the total functional configuration. So knowing a little bit about functional analysis and formulation, we can start looking at functional allocation. The decisions in the process of concept definition center on the selection of a particular system configuration or concept and the definition of the functions it is to perform. The systems engineering method calls for such decisions to be made by a structured process that considers the relative merit of a number of alternatives before any one is selected. This process is called trade-off studies or trade-off analysis and is used in decision-making processes throughout the system development. The predecessor system is a baseline. In cases where functions of the current system are same or similar to those of the new system, the current system provides a natural point of departure for system concept definition. Set of alternative approach will begin with a minimum modification of the system, restricted to those subsystems or major components that are clearly deficient. So those are the ones that we want to improve, if this is the case, that you're starting with a current or an existing system. Technological advances. Some new system developments are driven more by advances in technology than by operational deficiencies in the previous system. Such advances are often incorporated into an existing system to achieve specific performance improvement, and this is typical in the car industry. Some of the things that you can see is like modification of lights, or this of the lights of the car, or some modifications into the interior by integrating new technology on the dashboard, and that is an improvement in terms of technological advantage. If their impact is major, the possibility of a radical departure from the previous configuration should be included among the alternatives. Original concepts. Rare instances, a really different concept is advanced to meet an operational need. Not likely to be a previous system to use for comparison, and different type of alternatives will need to be examined. So in case that you don't have a predecessor system, then you're basically developing something from scratch, which is what we call an original concept. So in this type of project, then you're going to have to come up with multiple alternatives in order to examine the best strategy to follow. So this could happen like in examples such as projects that are required for NASA. NASA, most of their missions are new, so it's very hard to come up with a new system based on a predecessor, especially when things such as going to Mars are trying to be achieved. So in those cases, you might need to come up with an original concept or evaluate multiple original concepts to achieve the performance the performance required, and also to select the best alternative to move forward. Concept selection. So the objective of trade-off studies in the concept definition phase is to assess the relative goodness of alternative system concept with respect to operational performance and compatibility, program cost, program schedule, and risk in achieving each of the above. The results are judged not only by the degree to which each characteristic is expected to be achieved, but also by the balance among them. In terms of the program risk, the assessment of risk is another primary systems engineering task. Estimating the probability that a given technical approach will not succeed in achieving the intended objective at an affordable cost. Risk can be considered to consist of two factors. The first one, the probability of failure. This is the probability that the system will fail to achieve an essential program objective. And second one, the criticality of failure, which is the impact of the failure on the success of the program. A combination of the probability of failure weighted by its criticality to the system. So that's what we want to do. We want to combine those two. Conditions that may result in a significant probability of program failure include a leading edge on proven technology is to be applied, like you're trying to include a technology that hasn't been tested or hasn't been out for a long period of time, so you don't know how it will react. A major increase in performance is required, like you want to go for a throughput of 10 parts an hour to a throughput of 100 parts an hour in a manufacturing line. So that might have a risk that would result in a significant probability of program failure. A major decrease in cost is required for the same performance. A significantly more severe operating environment is postulated, and an unduly short development schedule is imposed. Finally, as part of this concept definition phase, we have the unified modeling language, which can help us understand the different components of our system and also the interactions that are required for our system with its surroundings and environment. So these are high-level models of system structure and behavior, which are used to gain understanding of how it may be configured to meet its requirements. So there are two groups of UML models, those structural diagrams and behavioral diagrams. Structural diagrams represent different views of system entity relationships, and the ones that we are going to discuss in class are the class diagram, which show a set of classes, their relationships, and their interfaces. And then the behavioral diagrams represent different views of system dynamic characteristics. And from those, we're going to discuss the use case diagram, which includes the interrelations among a set of use cases represented by system functions that respond to interactions with external entities, or what we're going to call actors. Sequence diagrams, they show the interactions among a set of objectives in executing a system scenario arranged in chronological order. State machine diagrams model the transition events and activities that change the state of the system. And activity diagrams are flowcharts of activities within a portion of the system showing control flows between activities. So this is an example of a use case diagram. Use cases have been used to assist the identification and analysis of operational and functional requirements. So as you can see here, as we discussed earlier, you have use cases that are those circles, and they have some actions in those circles, and then you can see the interaction between them and also with the actors outside the system. Modeling the interaction of an actor on the left side represented by the stick figures with a single use case represented by an oval, which leads to a subordinate activity or a separate use case, while the other three interact with a second external factor, in this case the library member. The arrows indicate the initiation of the use case, not the flow of information. For example, the librarian actor can initiate the management loads use case. The check-in book use case may also initiate the same use case. Each use case in the diagram represents a separate sequence of activities and events. UML, or Unified Modeling Language, defines a standard set of components for a use case, including the following list: the title, the short description, list of actors, initial or pre-condition describing the state of the environment before the use case occurs or is executed, end or post condition describing the state of the environment after the use case occurs, and the sequence of events, a list of actions or events that occur in a defined sequence. So this is the use case description for that first example. As you can see, at the top we have the short description, a list of factors, the initial conditions and the end conditions, and then after that we can see the sequence of events. Activity diagrams can represent any type of flow inherent in a system, including processes, operations, or control. The diagram accomplishes this through a sequence of activities and events. The sequence of activities and events is regulated by various control nodes. So this activity diagrams looks like a flowchart, and these are some of the definitions. You're not going to go through all of them, but these are the definition of some of the components of the basic activity diagrams. So here's an activity diagram for this librarian and library scenario. So this figure represents a simple activity diagram which is analogous to a functional flow diagram for our library book system. The diagram shows the activity path to split into two concurrent activities, one of which follows one of the two logical paths of returning or borrowing a library book. So those diagrams represent decisions or if, and then at this point that means that you are returning or borrowing. And then if you go to your left, we have the record return and the cancel loan. That's some activities. And then if you go to your right, you're into the borrow scenario, which conducts to a next decision whether you are over limit or under limit. And if you are under limit, you have two activities that can be performed. Sequence diagrams. These diagrams are usually linked to a use case where actions or events are listed in sequential format. The sequence diagram takes advantage of this sequence and provides a visual depiction of the sequence of events tied to the actor or subsystem performing the action. So here's an example. These represent a sequence diagram of the checkout operation. The diagram is tied to the use case presented below, but provides additional information over what's presented in the use case description. So for a sequence diagram, those lines that you see going from up to down, like those parallel lines, those are representing the timeline. So as you move down, that means those actions are happening after the actions that are happening above. And you can see also at the top you have the actor and you have those entities that are part of your system, like the checkout station, the loan management subsystem, and the book database. And those arrows that are going from column to column, those are the actions that are happening. So for instance, you have a message that says please swipe the card. So when the actor swipes the card, it moves to the checkout station. Checkout station reads the member's data from the card, and then there's a column going down that represents time, the time it takes to complete that action. And then it sends the request to the confirmed member. It's in good standing to the loan system, and they're going to check database for member information. So there's some information going to the database return confirming the good standing, and then sends confirmation back to the checkout station, and that information is then sent back to the actor, and the sequence diagram continues in that way. And then finally we have the class diagram. This is the heart of UML, is the concept of the class, and is depicted in the class diagram. The class is simply a set of objects that have the same characteristics and semantics. In this case, an object can be almost anything within the UML, can be represented in software. The class typically describes the structure and behavior of its objects. Within a class definition, three primary components exist: the attributes, which are the structural properties of the class, the operations, which are the behavior properties of the class, and the responsibilities, which are the obligation of the class. Classes typically have relationship with other classes. The basic structural relationship is known as an association. So figure 8.11 depicts a simple association between two classes, employee and company. The line linking the two classes can have an arrow. However, if no arrow is present, then a bidirectional relationship is assumed. The nature of the association can also be provided by using a triangle. The association is then read like a sentence. Employee works for a company and a company employs employees. Finally, if the author wants to designate the association as a numerical relationship, he can use multiplicity. Multiplicity designates the nominal aspects of the association and can be expressed with specific numbers or a series of shorthand notations. For example, 0.2 means that any value between 0 and 2 can exist as part of the association. The start symbol is used as a wildcard symbol and can be thought as a many. Thus, in our example, both the star and the number 1 are used to represent the fact that an employee works for only one company and the company employs many employees. So here's an example of a class diagram. Two other relationships types between classes and are generalization and dependency. Generalization refers to a taxonomic relationship between a special or specific class and general class. So figure 8.12, which is the figure in this slide, depicts a generalization relationship between the three classes: customer, corporate customer, and personal customer. In this case, both the corporate and the personal customers are specific class types belonging to the general class customer. This relationship is depicted as an arrow with a large arrowhead. In this diagram, the class attributes and operations are provided for each. When a generalization relationship is defined, the specific classes inherit the attributes and operations of the parent. Thus, the corporate customer class not only has its own attributes and operation, but would also contain the attributes name and address, in addition to the operation get credit rating. The same is true for the personal customer class. Dependency is the third type of relationship and denotes the situation where one class requires the other for its specification or implementation. We should note that dependency is a relationship type that can be used among other elements within the UML, not just classes. Here's another example. Here's include the dependency association with our library example. The class diagram depicts several association types as presents a number of classes that will be defined as part of the library checkout system. And this is the end of the lecture.